Let's see how to do the post-order traversal of a binary tree iteratively using one stack. Here we have a simple binary tree and we have a stack. So we begin by setting the current node to the root of the tree. And we will push it to the stack and set current to the left. Then again, current is not null. We push it to the stack and we set current to the left. Current is not null. Push it to the stack and set current to the left. This time the left of 4 is null. So what we do, we set current to the right child of what's on top of the stack. On top of the stack we have the 4. The right child of 4 is null, so current remains null. So what we do at this point is we set last equal to the top of the stack, which is 4. We pop the stack and we print last. Then we check, is last equal to the right child of what's on top of the stack? Because if that is the case, we are done with the right child of what's on top, so we can print what's on top. But in this case, 4 is not the right child of 2, it's the left child of 2. This means that we still need to process the right child of 2. So what we do now is we set current to the right child of 2. So the right child of 2 in this case is 5. We push it to the stack and we move to the left of 5. The left of 5 is null. So because current is null, we set current to the right child of what's on top of the stack. The right child of 5 is null. This means that we again set last to the top of the stack. We pop the stack, we print last, and we check, is last equal to what's on top of the stack right? The right child of 2 is 5, so that indeed is the case. So this means that we're done with the right child of 2, so we can now set last to 2, pop it from the stack, and print it. And then we again check, is last 2 equal to the right child of what's on top of the stack? 2 is not the right child of 1. We still need to process the right child of 1. So what we do, we set current to the right child of 1. We push it to the stack and we set current to the left of current. The left of 3 is null, so current becomes null. This means that we set current to the right child of what's on top of the stack. What's on top of the stack is 3, its right child is 6. 6 is not null, so we push it to the stack and we set current to the right child of 6. Again, it's not null, we push it to the stack and we set current to the left child of what's on top. To the left of current, I mean. The current is 7, its left is null. So now that current is null, we set current to the right child of what's on top of the stack. The right child of 7 is null, so current remains null. So we set last to what's on top of the stack, we pop it, and we print last. And then we check, is last equal to the right child of what's on top of the stack? The right child of 6 is null, so that's not the case. So what we do is set current to the right child of what's on top of the stack, so null. And because current is null, we go again and we set last to what's on top of the stack, 6, we pop it, and we print last. And then we check, is last equal to the right child of what's on top of the stack? 6 is the right child of 3, so we again set last equal to 3, we pop it, and we print it. Then we again check, is last equal to the right child of what's on top of the stack? what's on top of the stack is 1, and 3 is the right child of what's on top. So we're done with the right child of 1, so we set last to 1, we pop it from the stack, and we print it. Now this time we would check, is last equal to the right child of what's on top of the stack? But because the stack is empty, this indicates that we're done. If we look at the final output, we have 4, 5, 4, 5, 2, 7, 6, 3, 1, which indeed is a post-order traversal of this tree. Let's see how actually implement this. So we'll have a function called postorder, which is going to take the address to the root node, and we're going to return nothing. The first thing we're going to do is to initialize current equal to root. Now we don't need to check whether root is null because this case will be handled by the coded fellows, as we will see. Then we initialize our stack. And now we're going to enter a while loop from which we will exit within the body of the loop. The first thing we're going to do, we're going to check if current is different from null, and if it is, we're going to push it to the stack and move to the left. So if current is different from null, push it to the stack and move current to the left. Once current becomes null, we go to the else, and what we do in that case, as we saw, is set current to the right child of what's on top of the stack. However, we need to make sure that the stack is not empty, because if it is, this means that we're done. So if stack is empty, we break out a loop. So notice, therefore, that if a root was initially null, if we pass root null, we set current equal to null, then we enter the loop and current is null, so we go to the else, and because the stack is empty, we break out a loop. So we handle the case when root is null, and so we don't need to check that at the beginning of the function. So that's what I meant previously. All right, let's continue. So once we know that the stack is not empty, we're going to set current to the right child of what's on top. Now, if what's on top right was null, then as we saw, what we need to do, we need to print what's on top because there is no right. So if current is null, we will initialize last. We initially set last equal to null, as you will see right now. Why? And then we're going to have a loop. We're going to say, while the stack is not empty, and what's on top of the stack right is equal to last, we will set last to what's on top. We're going to pop the stack and print last. So in the code that we ran before, remember what we did, we initialized last immediately to the what's on top of the stack, and then we printed it. Now in our code, this is exactly what will happen, because when we set last to null, we see is stack empty. Stack is not empty because that's why we ended up here, because if it was empty, we would have broken out of the loop. Stack is not empty, and stack top right, which we know to be null because that's why we ended up here, is equal to last. Yes, it is. So we set last to the top of the stack, which is exactly what we did when we ran through the example. Then we pop the stack and we print last. And then again, we check. As long as the stack is not empty, because if it is empty, then in the case we're done. And what's on top right was equal to last. This means that we're again going to set last to what's on top. We're going to pop the stack and we're going to print it, which is exactly what we did in the example. And with that, we're done. So this is the entire function. So to make this more clear and to verify that the function actually works, we'll run through an example. So we again have the same tree we've seen before with root 1. So we call preorder passing root 1. We initialize current to root, so to 1. Then we initialize our stack as t, and then we're going to enter a while loop. So while current is different from null, we're going to push to the stack current and move current to the left. The left of 1 is 2. Again, current is not null, push it to the stack and move to the left. The left of 2 is 4. Current is not null, push it to the stack and move current to the left. The left of 4 is null, so current becomes null. Because current is now null, we go to the else and we check is stack empty. Stack is not empty. We set current to what's on top of the stack right. On top of the stack we have the 4, and the right of 4 is null, so current remains null. Then we check is current null? Current is null, so we're going to initialize last to null. And we're going to check while the stack empty, the stack is not empty. And what's on top of the stack, which is the 4 right, which is null, equal to last. Yes. We will set last to what's on top of 4. We will pop the stack and print last. And we're going to check again. Stack is not empty. And what's on top, which is 2 right, is 5. Is it equal to last? No, it's not. So we're going to exit the loop. So this loop will execute at least once, because stack, the very first time we enter it, enter this condition, stack is empty and what's on top right is equal to null, and which is equal to last, which is initialized to null. So one time this will execute for sure, and then eventually the second or third time we may exit this loop. So this time we exited after this the first iteration. So what we do now, we go back to the beginning of this loop and we check is current different from null. In this case, current is null. So we go back to the else and we check is the stack empty. Stack is not empty, so we set current to what's on top of the stack right. Because remember, when we check was last equal to the right child of what's on top, which was 5, that was false. So this means that now we need to explore the right child of what's on top. So we're going to set current to what's on top right. So the right of 2 is 5. And we're going to check is it null. It's not null. So we go back here, current is not null. We're going to push it to the stack and set current to the left. Current. So the left of 5 is null. So current becomes null again. And so this time current different from null is false. We go to the else. We check is stack empty. Stack is not empty. So we're going to set current to what's on top right. The right of 5 is null. So current remains null. So this is true. We can set last to null. Check stack is empty. Stack is not empty. And what's on top right is 5 right is null. It's equal to last, of course. The very first time this will always be true. We're going to set last to what's on top. Top of the stack is 5. So we're going to pop the stack and print last. We go back to the condition. Stack is not empty. And what's on top right? The right of 2 is 5. And this equals to the last. This indicates that we're done with the right of 2. So again, we enter the body of the loop. We set last to what's on top, which is 2. We pop the stack and we print last. We go back to the condition of the loop, stack is not empty, and what's on top, right, the right of 1 is 3, does not equal to last, which is 2. So we exit the loop, go back here, current is null, so we go to the else, so this means that we need to explore the right child of what's on top. So stack is not empty, and we're going to set current to the right child of what's on top, which is 3. Current is not null, so we go back here. It's not null, so we're going to push it to the stack and move it to the left. The left of 3 is null. Again, we go here, it's null, so we check is stack is not empty. We're going to set current to the right child of what's on top. The right child of 3 is 6. And we check is it null, it's not null. We go back here, it's not null, so we push it to the stack. We go to the left. The left of 6 is 7. Again, it's not null, we push it to the stack. And we move to the left of 7. The left of 7 is null. So current becomes null again. So current different from null, current is null, so we go to the else, stack is empty, stack is not empty. We're going to set current to what's on top right. The right of 7 is null, so current remains null. So this is true. Set last to null. And again we check stack is not empty, and what's on top right. The right of 7 is null, so it's equal to last. We set last to stack top, which is 7. We're going to pop the stack and print last. Then we go back here, stack is still not empty. What's on top? 6. Its right is null. This does not equal to last. So we exit this while loop, we go here, current is null, stack is not empty. We set current to what's on top of the stack right. 6 right is null, so current remains null. So this is again true. Last is initialized to null. And we check stack is not empty, and what's on top right, the right of 6 is null, so it's equal to last. We're going to set last to the top of the stack. 6. Pop the stack and print last. Again, stack is not empty. What's on top is 3. Its right is equal to 6, which is what last is. This indicates that we're done with its right child. So again, we enter the body of the loop. Last is set to stack top, which is 3. We pop the stack and we print last. Again, we go here, we check is stack not empty, stack is not empty, still has the 1. Is the stack top right? So the right of 1 is 3. Is it equal to last, which is 3? Yes, it does. So last is set to stack top, which is 1. Stack is popped, and last is printed. So this was 1. We go back to the condition. This time though, stack is empty, so this is false. We exit the loop, and we go back here. Current is null because every time we exit from this else, we left current set to null after this while, because if current was null, we entered here, we did not reset current, so this will always be null, as we can see right now. So again, it's not null. We go to the else, and we check is stack empty. Stack is empty this time, so we're gonna break out of the loop, and we're done. We exit here. So the output is 4527631, which indeed is the post-order traversal. Let's analyze the time and the space complexity. we do initially, let's start with the time complexity. Initially, we do some constant amount of work, some initialization, then we enter this loop. If we look at the body of this if, we know that this is the only place where we are pushing a value to the stack. And we know that every single node will be pushed to the stack exactly once. So this will execute once for every node. So if there are n nodes in the tree, this will execute n times, and this is all of one work. So the total work associated with this will be all of n. Then if we consider the else, this statement over here, when we move to the right child of a node, will again be executed once for every single node because we move to the right of a node exactly once. So this overall will be executed again n times, and all of one work is done. So if you do it n times, it will be all of n total work. Then this again will be true at most n times, since this is executed n times. This will be true at most n times, so we're going to set last to null pointer at most n times. So that's again all of n work. Now, the only question that remains, how much work is associated with this loop? If we consider the fact that all we're doing here, we're printing last will be some of the nodes, and this is the only place where we're printing them. We know that every single node will be printed only once, so again, this will execute n times, and the work associated with this is all of 1. So if we do it n times, it's going to be all of n. So therefore, overall, the time complexity will be all of n. What about the space complexity? It will depend on how will the stack grow. So if we look here, what we do, if current is not null, we're going to push it to the stack and move to the left. And we're going to keep doing this as long as current is not null. Once current becomes null, we go to the else, and we're going to set the current to what's on top right. And then again, while it's not null, we're going to keep pushing and then moving to the left. And once it becomes null, we go back to the right. So we go as deep as we can go. And if we reach the point where the right is null, that's where we're going to pop what's on top, and we're going to again move to the right and then start moving to the left. So therefore, the stack will at any point contain a path from the root node to a specific node, which in the worst case will be a leaf node, and in the worst case, this will be the longest path, which is going to be simply the height of the tree. So therefore, the space complexity will be O of h, where h is the height of the tree. So again, the time complexity is O of n, and the space complexity is O of h. You can find the link to the code in the description below.